Hello student, welcome to the wave optics course. Today we have lecture number 60 and in today's lecture we are going to discuss how polarized light can be produced. So, we have lecture number 60 today and today our topic is production of polarized light. So, any interaction of light with matter whose optical properties are asymmetric along the direction of the transverse of the propagation vector provide the means of polarization in fact. So, I am going to discuss what is the meaning of that. So, let me write any interaction of light. So, basically the production of the polarization light can be done by light matter interaction, but the interaction should be such that the optical properties is asymmetric. So, that is a major thing. So, let me write down any interaction of light with matter whose optical properties are asymmetric asymmetrical along the directions transverse to the propagation vector provides a means of polarize light. So, what I am trying to say is, suppose the light is propagating along this direction, that is k vector. So, something along this direction which is the transverse direction of the k, the optical property is asymmetric, that means it is not symmetric in nature. Then what happened, that there is a possibility this light matter interaction. So, this light matter interaction, so this is asymmetric optical property. Then in this light matter interaction one can get as polarized light as outcome. In general. So, meticulously we will going to discuss few cases. So, the most important process, there are few important process through which polarization can possible. I am just listing down here. The most well known or important process for polarization are dichroism, by means of reflection. One can polarize the light by reflection, scattering. One can also polarize the light by scattering and by refringence. So, roughly these are the techniques that are used to get the polarized light. So, let us start with this dichroism system. So, simply a most simple case I am going to discuss here. And the most useful example, that is the wire grid polarizer. So, suppose I have concept is this, I have a system and here these are the lines suggest that these are thin copper wire. It is making a net like this. And an unpolarized electromagnetic radiation, when I say unpolarized, that means the polarization is not defined, it can be any direction, and I can write it like this. This is unpolarized light, and I am going to get at the outcome, I am going to get a polarization like this. Why? I will discuss. This is a polarized light. So, when a unpolarized electromagnetic wave vector is incident on a system of this thin copper. So, this is a system with thin copper wire placed parallel to each other. The E along the length of the horizontal wire, that is this, is absorbed, is they are mostly absorbed here, and the horizontal component does not do any work here. The horizontal component does not work on the electrons that is distributed over this wire. So, what happened that the horizontal component will be exhausted with this system, where the vertical component will not going to do much work. So, no absorption will be there. So, vertical component will pass through. So, that means with a very simple way we can do that that kind of polarization. But for effective polarization, the spacing between the wire should be very small, and that should be even less than lambda. So, there are few, so what the horizontal component will do. So, this is the system, and these are the wires. I am drawing in a magnified version. So, two components, any vector can be divided into two components, one is vertical and another is horizontal. So, this horizontal component will take part in, because it is having the, it is parallel to this, it is having the same alignment. So, this component will be used here to make joule heating, and it will be absorbed by these wires, and that is why this component will no longer be there in the outside. In the outside means in this region, it is the output. The vertical component, which is not exhausted, which is not utilized much throughout when it is passing through the system, will remain unchanged and will get this kind of polarization at the output. This is a way we can simply polarize the light, but the problem is the effective polarization of the space, the effective for efficient polarization, this spacing should be much less than the wavelength use, that is lambda. So, making the spacing with that amount is very difficult actually by using the copper wire. So, for microwave it is okay. So, for microwave this kind of system should be useful, where we can make the spacing of the order of wavelength, and microwave can be polarized. But for visible light, the lambda is very small, and it is very difficult to formulate this kind of, to generate this polarization through this system. So, Polaroid are used for that. So, there are systems which is called Polaroid. So, in Polaroid what happened is these are a sheet containing long chain of polymer molecule, acts like this copper wire. That aligned parallel to each other. So, Polaroid is a sheet where these polymer molecules are aligned parallel to each other, and this light component parallel to the alignment of the this polymer chain get absorbed in the same way that we discussed, and the perpendicular component will be transmitted. So, the same system we are using here, but instead of putting copper wire with the spacing of the order of lambda, instead of doing that we are using Polaroids that naturally gives us this kind of system where the polymer molecules are arranged. So, the pass axis is accordingly defined, and that is the direction through which the light is polarized, and if we have a polarizer here, two polarizer placed side by side here, or this polarized plate we place like this, and whose path axes are perpendicular to each other, then if I produce a light here, the first case, a unpolarized light get polarized first after passing through polarizer, and then if we rotate this another Polaroid film we have, and if we rotate this 90 degrees so that its path axis is now perpendicular to the previous one, then here we do not get any light. So, there will be no light. So, this is the first one is generally called the polarizer, and since we analyze the state of the light, we called it analyzer. We call it analyzer. So, this is the way we can do, and not only that, we can rotate this analyzer, and when we rotate this analyzer, so few amount of light one can get. If it is exactly perpendicular, then we will not going to get. If there is a angle between the two path axis, then we get something. So, that basically leads to something very interesting called Malus law. So, in Malus law again we have our polarizer sitting here, whose path axis is like this. This is the path axis, and we have another polarizer here which analyze the light. So, we can call it an analyzer as well. And anyway, this line is and we have the path axis along this. So, let me draw the path axis in different color, maybe in green. So, this is a direction, path axis is essentially direction, and this angle is say theta, and then I try to find out what is the intensity at this. So, this is again a polarizer, and this is analyzer. Unpolarized light is passing through this system, and we get a polarization here, and now I have a path axis which is not perpendicular to the polarized direction of this polarization, but having an angle theta to the previous one. So, in that case, if I have intensity here I naught. So, the intensity that I will get the output is I naught cos square theta, that is the Malus law. So, I will be I at this point will be I naught and cos square theta. So, if somebody plot what happened with the theta, then the intensity will going to change in this way, the cos square function. So, 0 and this is pi by 2, this is pi, this is 3 pi by 2 and this is 2 pi and so on. So, that means if I start rotating these things, if I start rotating this entire thing, then this is the way the intensity will vary, and intensity is essentially function of theta. So, I will get I theta is equal to I naught cos square theta, and that is my Malus law. That is my Malus law. So, next we will discuss how to polarize the light by reflection. So, that is also an interesting thing. So, polarization by reflection. So, what happened, and in few cases we find that, suppose, okay, let me draw this figure first. So, after having the Malus law, now we will check that what happened if I just simply allow the light to reflect from a surface, and after reflection what is the state of polarization. Okay. So, there is a incident light and then there is a reflected light and refracted light. So, refractive index here is N1 and it is N2, and components are there. These are the components which is perpendicular to the page of paper. So, I launch it. So, the electric field is vibrating as the perpendicular to the page of paper, that is why I put it dot. Another case one can consider, this is case 1. Same thing, we have light that is launched here, we have reflected light and we have transmitted light. It is coming like this and this. These are dielectric surface. So, refractive index is N1 and N2 here, but here the refractive index. So, this is called the ES field, where electric field is vibrating perpendicular to or parallel to the surface. I mean, it is vibrating parallel to the surface, but here the electric field is vibrating along this direction. It is reflected. This is case, and what happened that for a specific angle, if these two components are there, let me first draw it. So, now both the components are together. Sorry, because it is now, it will going to polarize now. So, this component will not be there here. We have this component. So, the reflected component will no longer have the this. So, here this field is called EP, and this is a specific angle for which we have this, we call it theta p. It is called the boosted angle for which. So, this is case 2, this is figure 3, N1, N2. We are going to discuss this actually. So, the reflection of the T mode, the transverse electric mode, this case that we are getting here. So, this is reflection of TE mode, where T means transverse. Let me write it. Transverse electric mode, where beam ES is perpendicular to the plane of incidence. So, the plane of incidence is this paper, so it is perpendicular to that. Now, here we get this figure, we get reflection of TM mode, where TM is transverse magnetic mode, where beam EP is in the plane of the electric field, actually in the plane of incidence. It is perpendicular to the plane of incidence, it is a parallel to the plane of, or on the plane of, is in the plane of incidence. And this case, the incident beam contains both polarization. Contain both polarization. Now let us see what happened for this case. So we have this system and the light ray is falling here, and then this is EP, this is the reflected ray, and this is the transmitted ray. Now in the transmitted ray there will be vibration along this direction, and we have reflection. If I draw the parallel to the reflection, so this angle is making an angle now, and this angle is theta. So now what happened inside the system, it tried the dipole to oscillate. So the dipole, so this is the dipole axis. So dipole will going to inside the material, because the dielectric dipole will going to oscillate. So dipole axis. So now the dipoles will going to oscillate dipole oscillation along EP field. So dipole, so this oscillated dipole will going to radiate, and this radiation will be the dotted line which is along the reflected direction, and that oscillation, it will going to oscillate, and because the light is coming this way, so the dipole radiates along the dotted line, which is along the reflected ray direction. With intensity I as a function of theta, and that is proportional to sine square theta. That one can get from dipole oscillation theory. So the dipole when they are oscillating, it will radiate, and this radiation, as I shown, depends on the value of the theta with the dipole axis, So, that means along this dotted line it has a maximum intensity, and this intensity will reduce along the direction of the dipole. So, note so here, if that means if these if this vibration, this dipole axis is such that so let me do that here. So, note when the angle between, so let me draw it once again here, maybe here I can draw quickly. So, this angle is theta p. My drawing is not and here this is theta t and this is the vibration we are having. So, note that when these two are, so note when the angle between the reflected and transmitted ray is pi by 2, that is I am talking about this angle, the different color maybe, I am talking about this angle. When it is pi by 2, then some special thing is happening here. Then there should be no, because this vibration was due to EP, so there should be no EP components. So, this vibration was due to EP, so EP component will no longer be there. So, the refracted ray will only contain the ES1 EP component in the, so there should not be no EP component in the reflected ray. So, there should not be any EP component, because then what happened, that the radiation due to dipole will be 0 for EP, as sin theta will be 0 now. Okay. So, now from Snell's law, under this condition I can write, so this is my N1, this is my N2, so that is the condition we are getting these things. So, from Snell's law what I get? We get N1 sin, so this is theta p. So, N1 sin theta p will be N2 sin of theta t. That is the condition we are getting. So, theta p, you can, if I look carefully here, then this and this is, this plus this is 90 degree and this is 90 degree. So, theta p plus theta t is 90 degree. Theta p plus theta t is equal to pi by 2. If that is the case, we can get the expression N1 sin theta p will be N2 cos theta p, or tan theta p can give us N2 divided by N1, or theta p will be simply tan inverse of N2 by N1. So, this is the angle. If I launch the light in that particular angle, having the knowledge of N2 and N1, then I can partially polarized the light. So, this angle is called the Brewster angle. So, by using this theory, we can see that we can get a light after reflection which is partially polarized. So, I do not have much time to discuss more today. So, whatever we discuss is how to polarize the light with different system, and then we discuss that by using the reflection also we can polarize. So, in the next class what we do is we will going to discuss the other two way to polarize the light. One is by scattering and another is by using the birefringence property of a crystal. That is interesting. So, see you in the next class, and thank you for your attention.